Hello students, in the previous sections I have studied about the addition of vectors, component of vectors, and then we are going to discuss about the multiplication of a scalar with a vector, multiplication of two vectors, etc. under vectors. And there are three different kinds of products which we are going to speak out. One is scalar multiplied with a vector. What will be the result? Will be a vector. Second one, a vector multiplied with another vector may give you a scalar, and a vector multiplied with another vector will give you a vector. There is another one thing. Can multiply a real number with a vector, then you will get the vector itself. We shall see one by one. If a real number is multiplied, or otherwise I can write it as multiplication of real number with vectors. Multiplication of real number with vectors. If suppose a real number is multiplied along with a vector, a vector, if the number that has to be multiplied along with a vector is 2, then the resulting vector or resulting quantity will be 2a vector. So what has happened is that the magnitude of the vector increased by 2 times, but the direction of the vector remains same, and then the unit of the vector remains the same. The unit of the vector remains the same. So when a vector is multiplied along with a real number, then the magnitude of the vector increases, but the direction of the vector remains same. The unit of the vector also remains the same. For example, I can write a vector which is represented as 2i plus 3j vector. Then this must be multiplied along with the 3a vector. Then what will be the result? I can take it as 1, 2, 3, 1, 2, 3. Then 2i, this is the x coordinate and this one is y coordinate. 2i is represented here and 3j is represented here. When these two are connected, then this is the a vector. This is the a vector. What is 3a vector here? A vector must be multiplied along with the 3. So 3 into 2i plus 3j vector. So this is 6i cap plus 9j cap. Then the vector will become 1, 2, 3, 4, 5, 6. What is required? 6i. So I am marking 6. And then 1, 2, 3, 4, 5, 6, 7, 8, and then 9 along the y direction. So when you connect these 2 points, then the vector is going along the same direction. You can see that. The vector is going along the same direction. So there is no change in the direction of this 3a vector. So this is 3a vector. There is no change in the direction of 3a vector, but its magnitude has changed. A vector becomes 3a vector and its unit remains the same. This is about the multiplication of real number with a vector. What will happen if you multiply a scalar with a vector? If you multiply a scalar with a vector, you can see here, okay, just leave it here. We shall go on to the other heading, multiplication of scalar with vector. Let us consider a scalar quantity, let us say time, which is expressed in terms of second, and then a vector quantity velocity, which is expressed in terms of meter per second. When this time is multiplied along with the velocity, then you will get a TV vector. So what has happened? The vector whose magnitude increases by t times. So the magnitude of the vector increases by t times. What about the direction direction remains same. Direction remains same as that of v vector. What about the unit of this vector? Unit of the vector will change. Unit of the vector will change. Unit of time is second, unit of velocity is meter per second. The second gets cancelled out, so this will become meter. So unit of this quantity will become meter. So when you multiply a scalar with a vector, the resulting quantity will be a vector. Let us consider this as x. X will be a vector. Resulting quantity will be a vector. Its magnitude increases by t times, its direction remains the same, and its unit changes. I can give you an example here. If I write F is equal to ma, F is equal to ma, mass is a scalar quantity, acceleration is a vector quantity, force is also a vector quantity. So when a scalar multiplied with a vector gives you a vector. Also, you can write F is equal to QE. There is a difference here. Mass is a scalar, charge is a scalar, but in this product, force acts always along the direction of acceleration. But in the second case, force will be acting along the direction of the electric field, depending upon the nature of the charge. Charge may be either positive or negative. If charge is considered positive, then force acts along the direction of electric field. If charge is considered negative, then the force will be acting in a direction opposite to that of the electric field. We are going to start the multiplication of a vector with another vector. As I told you already, a vector multiplied with another vector may give you a scalar or a vector. If the resulting quantity is a scalar, then this product of two vectors is called a scalar dot product. So we are going to discuss about a scalar dot product, scalar product or dot product or inner product. Inner product. So a scalar product can be expressed as scalar product or dot product or inner product. Sometimes we used to call it as scalar dot product. What is a scalar product? If two vectors are taken a product, a dot product or a product, if the resulting quantity is a scalar, let us say C, then this product is termed a scalar product. This product is termed a scalar product. If A vector is taken, a product with the B vector, a dot product is carried out, then the resulting quantity is a scalar, then this vector product can be represented or mentioned as a scalar product or a dot product or a inner product. For example, force vector when multiplied with a displacement vector gives you a work done. Force is a vector quantity, displacement is a vector quantity. They are taken a dot product. The resulting quantity is work done, which is a scalar quantity. So, if two vectors are taken a product, dot product, the resulting quantity is a scalar, then the product is called a scalar dot product. So, how will you define scalar dot product? Scalar dot product is defined as the product of magnitude of, you can represent it here. A vector dot B vector can be represented as modulus of A vector, modulus of B vector into cosine of the angle theta between the two vectors. I can say if two vectors A vector and B vector are acting by making some angle theta, then our dot product of these two vectors is equal to the magnitude of A vector and magnitude of B vector and the cosine of the angle theta between the two vectors. Cosine of the angle theta, which angle you have to take here? Two angles are coming here. Which angle is considered? The smallest angle theta between the two vectors. So, a scalar dot product is defined as the product of magnitude of the two vectors, A vector and B vector, and the cosine of the angle theta between the two vectors. Also, we can represent in another form that if two vectors are taken, one is A vector, another one is B vector, theta is the angle between the two vectors. If a perpendicular is drawn, or a component is resolved for this B vector, which is going to act along A vector, I can say this as B cos theta. B cos theta. When you take a dot product, A vector dot B vector, then this can be represented as either A into B cos theta, or we can say B into A cos theta. How will you define this? It is the product of magnitude of one vector and the component of another vector along the direction of first vector. See this one? It is the product of a vector A with the component b cos theta, which is acting along the direction of the first vector. So I could say the dot product of two vectors is equal to the product of one vector along with the component of the second vector acting along the direction of the first vector. If you take the perpendicular component or vertical component as b sin theta, then b sin theta is acting perpendicular to a. Which one is acting along the direction of a? B cos theta. So first vector must be taken as a product with the component of the second vector acting along the direction of the first vector. So a into b cos theta. Or otherwise, we can say here, if a vector and b vector are taken, if a perpendicular or a component is resolved for a vector, then we can say this is a cos theta, so we can represent b into a cos theta. So, three different ways by which we can define a scalar dot product. A scalar dot product is the product of magnitude of a vector and b vector multiplied by cosine of the angle theta between the two vectors. The second case, you can say a vector multiplied with the component of the second vector which is acting along the direction of the first vector gives you the dot product of the two vectors, which is also a scalar dot product. So a general representation is that if a vector dot b vector is taken, if two vectors are taken dot product, then the resulting value will be a vector modulus of a vector modulus of b vector cos theta, or else you can simply write ab cos theta, which has only magnitude and has no direction. Which has only magnitude and has no direction. That is why this dot product is termed a scalar product. Now, we shall speak about the properties of the scalar dot product. Properties of the scalar dot product. First one, dot product of two vectors, a vector dot b vector, will give you a quantity c, which is always a scalar in this case. In a scalar dot product, if a dot product is taken, the resulting quantity will always be a scalar. And the scalar may either be positive or negative or zero. When do we say this dot product is positive? When the angle theta between the two vectors is acute, less than 90 degree. When the angle theta between the two vectors is acute, which is less than 90 degree. When do we say the two vectors will give you a negative value? Then the value of theta must be greater than 90 degree or less than 180 degree. Less than 180 degree. Which means if it is an obtuse angle, then the scalar quantity will be a negative quantity. If the value of theta between the two vectors is 90 degree, then we can say here the product of dot product of these two vectors will be equal to 0. So the resulting quantity of a dot product is always a scalar. The scalar quantity may either be positive or negative or 0. It is positive when the two vectors are making an angle theta which is less than 90 degree. That is, it must make an acute angle. And it is negative, the dot product is negative if theta lies between 90 degree and 180 degree. So the angle between the two vectors must be an obtuse angle. If the two vectors are at right angles to each other, then we can say the resulting quantity, scalar quantity, is always a 0. So we can say these two vectors, a vector and b vector, will result in a quantity which is positive because it is acute. These two vectors will give you a negative value because this is obtuse. And in this case, in the third case, the two vectors are at right angles, so the resulting quantity will be 0. This is the first property. Second property is that the product of two vectors obeys commutative law, or the scalar product obeys commutative law. So we can say here the scalar product of two vectors obeys commutative law. It's commutative. That is, a vector dot b vector is equal to b vector dot a vector. We can see here, if two vectors are taken a dot product, a vector and b vector, they are making some angle theta. A towards B, so I am undergoing an anti-clockwise directional motion, anti-clockwise direction. So A vector dot B vector is equal to AB cos theta. Here I consider theta as positive quantity. Theta is a positive one, because this is an assumption. If I am taking, or if I am moving in the anti-clockwise direction, I am taking theta as a positive value. If B vector dot A vector is taken, then the theta is measured in a reverse order, so theta must be negative. So once again, if I write B vector dot A vector, then this is B A cos of minus theta, because theta is negative, because I am going in the clockwise direction. Theta is negative. So cos of minus theta is cos theta itself, even function. So we can have BA cos theta. So if you compare these two expressions, A vector dot B vector and B vector dot A vector, you have AB cos theta, BA cos theta. AB is simply magnitude. So 1 into 2, 2 into 1, both are same. So AB cos theta and BA cos theta are equal. So scalar dot product is commutative. A vector dot B vector is equal to B vector dot A vector. The third property of scalar dot product is this one. Scalar product of vectors is distributive, or they obey distributive law. Distributive. You can say here A vector dot B vector plus C vector is equal to A vector dot B vector plus A vector dot C vector. So it obeys distributive law. Fourth one, how will you determine the angle between the two vectors? The angle between the two vectors can be given by theta equals cos inverse of A vector dot B vector divided by modulus of A vector modulus of B vector. Modulus of A vector modulus of B vector is nothing but magnitude of the vectors. So I can write A vector dot B vector divided by AB. So theta can be calculated using this expression. Theta equals cos inverse of A vector dot B vector divided by AB. So this is the fourth property. Now we shall go on to the fifth property here. When do we say the dot product of two vectors is maximum? The dot product of two vectors is maximum. A vector dot B vector is maximum when the angle between the two vectors is 0. If theta is 0, cos 0 is 1. Then the dot product can be represented as A vector dot B vector is equal to AB cos theta, which is AB into cos 0 is 1, so simply AB. So A vector dot B vector is maximum and it is equal to AB when theta is equal to 0. This is applicable in most of the physics fundamentals, so you should know this. If two vectors are acting along the same direction by making an angle theta equals 0, then cos 0 is equal to 1 as per trigonometry. Then A vector dot B vector is maximum, which is equal to AB. Now, the sixth property, when do we say the dot product of the two vectors is minimum? The dot product of the two vectors is minimum when the two vectors, A vector and B vector, are acting by making an angle of 180 degree. If the two vectors are acting by making an angle of 180 degree, then the dot product of these two vectors is said to be minimum. How? We can write A vector dot B vector is equal to AB cos theta. So this is AB cos 180. Cos 180 is minus 1. So minus of AB. So A vector dot B vector is minimum, which is equal to minus AB. So these are all the conditions. When do we say the dot product of two vectors is minimum? When the two vectors are acting by making an angle of 180 degree. When it is maximum, when they are acting along the direction, same direction. And the seventh one is that if two vectors are acting at right angles to each other, If A vector and B vector are making an angle of 90 degree between them, then the dot product of these two vectors A vector dot B vector is equal to AB cos 90. Cos 90 is 0. So the entire term goes as 0. The dot product of the two vectors will be 0 or is equal to 0 when the two vectors are acting by making an angle of 90 degree. If this happens, then we can say the two vectors are mutually orthogonal. These two vectors A vector and B vector are mutually orthogonal. So we can say it is mutually orthogonal. This is a special condition, orthogonality of vectors. When do we say two vectors are orthogonal? When they make an angle of 90 degree. When the two vectors make an angle of 90 degree, then we can say the two vectors are mutually orthogonal. So what is the dot product of mutually orthogonal vectors? 0. Dot product of mutually orthogonal vectors? 0. We can simply show it here with a simple example. Let us speak about electric flux here. Electric flux is represented with the phi vector equals E vector dot ds vector or dA vector. E vector, electric field vector. ds vector, area vector. Phi is the flux. The dot product of these two vectors gives you flux. They will ask you, when will you get a maximum flux? Then you can say, when the electric field vector and area vector are acting along the same direction. Simply, I can show you. This is the area, cross-sectional area, and this is the area vector, ds vector. This is ds, and this is ds vector. And electric field is acting along the same direction. Here, electric field and ds vector are making an angle 0. So the flux is said to be maximum. What is the maximum flux? Phi equals E into ds. If suppose you are calculating minimum flux, then what should be the case? We can simply say here ds vector acts along this direction. Electric field vector must act in the opposite direction. The angle between the two vectors is 180 degree. So the flux is minus of EDS. Flux is minus of EDS. Then when will you say flux is 0? When the area vector is acting along this direction, field vector is acting along this direction. The two are at angle 90 degree, then the flux is said to be 0. This is a simple case here. This is a simple example. So we can have a positive value, a negative value, or even a 0 value in case of scalar dot products. It all depends upon the angle made between the two vectors, or angle between the two vectors. If the angle between the two vectors is 0, then we can say the dot product of the two vectors is maximum. If the angle between the two vectors is 180 degree, then the dot product of the two vectors is minimum. If the angle between the two vectors is 90 degree, then the two vectors are mutually orthogonal. Orthogonal here refers to the perpendicular vectors. Orthogonal vectors refers to perpendicular vectors. Two vectors are acting perpendicular to each other. Perpendicular to each other. Each other is termed mutually. With respect to B, A is at 90 degree. With respect to A, B is at 90 degree. This is termed as mutually orthogonal condition. So, this is the 7th point related to scalar dot product. Next property. The scalar dot product of a vector with itself. The scalar dot product of a vector with itself. A vector is taken a dot product with the same A vector. Is called self dot product. Is called self dot product. So we can say here A vector square is equal to A vector dot A vector. How will you represent A vector dot A vector? Magnitude of A vector. Once again magnitude of A vector cos of the angle theta between the two vectors. Since A vector is taken a product with A vector, these two vectors will be acting along the same direction. Simple. If I say, or if I represent the coordinate axis x, y, z, this is I cap, this one is j cap, and this one is k cap. These are all the unit vectors. If I am taking I vector as a dot product with another I vector, what does that mean? The two vectors are acting along the same x direction. In the same way, if A vector is taken a dot product with another A vector, then this gives a condition that the two vectors are acting along the same direction. If two vectors are acting along the same direction, then theta is equal to 0. What is cos 0? 1. So we'll have simply A into A. So this is A square. A square. So A vector square or A vector dot A vector is equal to A square. So we can simply say the magnitude or norm of a vector. Norm of a vector. Magnitude or norm of a vector is given by A square is equal to A vector dot A vector. So A equals square root of A vector dot A vector. A equals square root of A vector dot A vector. So the magnitude or norm. Norm is also representation of magnitude. Magnitude of a vector. What is magnitude actually? Value. The value of a vector. Because a scalar quantity has only magnitude, no direction. Which means it has only value, no specific direction. So magnitude or norm of a vector is A equals square root of A vector dot A vector. So what is the self dot product? If a vector is taken a scalar dot product with itself. With itself. In the sense it is taking a dot product with the same vector. Then the product is called the self dot product, and the self dot product is represented as A vector square is equal to A vector dot A vector, which is A cos theta. Why I am taking this theta as 0? As I told you, this A vector dot A vector, which means the two vectors are along the same direction. They are acting along the same direction, which means theta is 0. Cos 0 is 1. So the product will give you the result A square. And the magnitude or norm of a vector is A equals square root of A vector dot A vector. Now, the ninth property is that in case of unit vectors, let us say n cap, if I represent a vector with a cap or hat or caret, then it is called unit vector. In case of unit vector, I can write n cap dot n cap is equal to 1. N cap dot n cap is equal to 1 because this is a unit vector. N cap is taken as its magnitude. Another n cap, its magnitude n. What is this n? Unit vector. Unit vector in the sense it has single magnitude, 1. So 1 into 1, cos of 0 is also 1, so simply 1. So a unit vector is taken a dot product, then the resulting value is said to be 1. So in case of this coordinate axis, in case of these unit vectors along the coordinate axis, I can say if I vector is taken a dot product with another I vector, if j vector is taken a dot product with another j vector, and k vector is taken a dot product with another k vector. These are all unit vectors. If a unit vector is multiplied with another unit vector by undergoing a dot product, then the resulting value is 1. So I dot I is 1, j dot j is 1, k dot k is 1. I dot I is 1, j dot j is 1, k dot k is 1. Which means you are taking a dot product of one vector in x direction with another vector along the same x direction. Then the resulting value is said to be 1 when the two vectors are unit vectors. And j dot j is also 1, k dot k is also 1. These conditions are all very important while solving problems. Now, the next property, 10th property, is that in case of orthogonal unit vectors, which one is called as orthogonal unit vector? I can take this as I cap, this one as j cap, and this one as k cap. I and j are at right angles to each other. J and k are at right angles to each other. K and I are at right angles to each other. So, these three vectors are orthogonal unit vectors. In the case of orthogonal unit vectors, which means if you take a dot product of I vector with the j vector and j vector with the k vector, j vector with the k vector, then k vector with I vector. So I can show like this. In this case, k vector with the I vector, in this case the dot product whose value is equal to 0. So in case of orthogonal unit vectors, the dot product of these two vectors, orthogonal unit vectors, is 0. As we saw in the earlier case, that when two vectors are mutually orthogonal, then the angle between the two vectors is 90 degree. So cos 90 becomes 0, so the dot product of the two vectors will become 0. So in case of unit vectors, like n cap, the dot product of unit vectors is equal to 1. I dot I is 1, j dot j is 1, k dot k is 1. Whereas in case of orthogonal unit vectors, when the same vectors are taken at right angles, I vector and j vector are taken at right angles, then the dot product of the two vectors is equal to 0. I dot j, j dot k dot I are all equal to 0. Then the 11th property is that if the dot product of the two vectors is represented in terms of components, if the dot product of two vectors is represented in terms of components, then what will be the form in which we will be representing the dot product of two vectors in terms of components? A vector in all the three dimensions can be represented as ax I cap plus ay j cap plus az k cap. In the same way, b vector is equal to bx I cap plus by j cap plus bz k cap. When this a vector and b vector are taken a dot product, then what will happen? I dot I 1, j dot j 1, k dot k 1. If I goes with j, I goes as a dot product with k, then their values will be 0. Then j with I, j with k will be 0. K with I, k with j will be equal to 0. Similarly, this b with a components are I with jk, j with ik, and k with ij. These products will be equal to 0. So what will be the result here? I dot I alone, or otherwise I can write the entire terms which are all involving in this dot product. I can write ax I cap dot bx I cap plus ax I cap dot by j cap plus ax I cap dot bz k cap. Similarly, for ay j cap dot bx I cap plus ay j cap dot by j cap plus ay j cap dot bz k cap, and then az k cap dot bx I cap plus az k cap dot by j cap plus az k cap dot bz k cap. If you look at this dot products, I dot I is 1, I dot j is 0, I dot k is 0. Similarly, j dot I is 0, j dot k is 0, k dot I is 0, k dot j is 0. Simply what will be left? Ax dot bx, ay dot by, then az dot bz. I dot I is 1, j dot j is 1, k dot k is 1. So the dot product of these two vectors, a vector dot b vector, whose in terms of components is ax bx plus ay by plus az bz. And the magnitude of a vector is a equals square root of ax square plus ay square plus az square. Magnitude of b vector is b equals square root of bx square plus by square plus bz square. This is the representation of the dot products in terms of its components. Then the component of b vector along a vector is b cos theta. As I showed you earlier, a vector, this is b vector, this is the component of b vector along a vector, which is b cos theta. So this can be taken as b cos theta into a divided by a. I am multiplying and dividing by a. AB cos theta is nothing but a vector dot b vector divided by a. A vector divided by its magnitude is unit vector. So a cap into b vector. A cap dot b vector. So this is the component of b vector along a vector. Similarly, component of a vector along b vector is a cos theta, which is a into b cos theta divided by b. I am multiplying and dividing by b with this quantity. So I will have a vector dot b vector divided by b. A vector divided by its magnitude is its unit vector. So b cap, a vector dot b cap. So if they ask you to calculate the component of A vector along B vector or component of B vector along A vector, then you can go directly A cap dot B vector. In this case, it is A vector dot B cap. We shall see the example 2.8. Check whether the two vectors are orthogonal. You are asked to calculate or to check whether the two vectors are orthogonal. What is the condition for orthogonality? The product of the two vectors must be equal to 0. So if you take a dot product of A vector and B vector, which gives you a result as 0, then the two vectors are said to be orthogonal. I am doing the first one. A vector dot B vector is equal to 2i into 4i. So it is 8, I dot I is 1. And 3j minus 5j, 3j minus 5j, so minus 15, j dot j is 1. So 8 minus 15 is said to be minus 7. This is not equal to 0. So this dot product of the two vectors are not orthogonal. Whereas in the second case, I am taking C vector and D vector, C vector dot D vector, 5i and 2i are taken a dot product, 5 into 2, 10, I dot I is 1. 2i and 5i are taken a dot product, so 2 into 5, 10, minus 10, j dot j is 1. Unit vectors also have to be taken a dot product, j dot j is 1. So it goes off. So 10 minus 10 is 0. So C vector dot D vector is orthogonal. C vector dot D vector is orthogonal. You can represent it in a graphical form also. X minus x, y minus y. For A vector dot B vector, I can represent A vector is 2i plus 3j. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This one is 1, 2, 3, 4, 5. Let us say this is origin. So I can represent A vector as 2i plus 3j. This is 2i, this is 3j. And this is A vector. Then 4i minus 5j, I is 4, 1, 2, 3, 4. 4i minus 5j, 1, 2, 3, 4, 5, minus 5j, minus y. So in the negative direction, you are taking the point. So this is B vector. These two are not at right angles. These two are not at right angles. Whereas in the case of C vector dot D vector, I can show with the same diagram so that it will be simple. Five I plus 2j, this is 1, 2, 3, 4, 5. 5i plus 2j, this is C vector. Then D vector is 2i minus of 5j, 2i minus 5j, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, this is at right angle. So, with the diagram also, with the geometrical representation also, we can show that these two vectors are orthogonal and these two vectors are not orthogonal. Another example is also there in your textbook. You can just go through it, which is very simple, right? Then, next thing is that we can give out an example for a scalar dot product. We are having so many number of examples. Work done is 1, W equals F vector dot S vector. Then flux is there, E vector dot ds vector. Also we have magnetic flux B vector dot ds vector or dA vector. There are so many number of examples for a scalar dot product. You can say work done is positive or negative or even 0. When the force and the displacement are acting along the same direction, work done is positive. When force and displacement are acting along the opposite direction, then the work done is negative. When force and displacement are at right angles to each other, work done is 0. These ideas are very much important while you go through the fundamentals in +2 syllabus, even in +1 syllabus also, right? So it is necessary to go through all the properties of scalar dot product. That will be much helpful in your further studies. Thank you.